A parallel beam of light of wavelength 600 nanometer is incident normally on a diffraction grating, and the grating has 300 lines per millimeter. What is the total number of intensity of maxima from the grating? Or let's first understand how diffraction grating, how beam of light behaves when it falls on normally on a diffraction grating. So imagine this is our diffraction grating, and this got very tiny little gaps between the vertical lines on this diffraction grating, and these are tiny little gaps that allow the diffraction, okay, which is actually acting like a partial blockage for the wave, and that's the condition which enables diffraction. So when light falls perpendicularly on this diffraction grating, it diffracts. All right, it diffracts, and this diffraction will cause a fringe pattern to appear here. Okay, you will get number of maximas and minimas on the screen. All right, you will get number of maximas, which are the bright points. Okay, which are the bright points, and these dull points are representing the minima. And the main formula for this experiment is n lambda equals to d sine theta. All right. So if this is the screen, and these are number of maximas. This is maxima 1, maxima 2, maxima 0, maxima 1, and then maxima 2. So these are like mirror images of each other. So the center point of maxima, then above the center point and below the center point, you will be getting mirror images. And this, for example, if I'm talking about this maxima number 2, so this theta will be this theta, and n will take this value 2. Lambda will be the wavelength of the wavelength of the light you have shown on the diffraction grating, and d represents the. All right, so d is the main thing. So d represents the gap between the slits. All right, so there are, all right, not the slits, we can say the gap between the lines, on the diffraction grating. All right, this is d. So to calculate the total number of maxima, we will keep sine theta as 1. Okay, because sine theta can maximum take value of 1, so we'll keep sine theta as 1, and our new formula will become, because we need to find the total number of maxima, so we will keep sine theta as 1, and we'll figure out the value of n. So n will be equals to d over lambda. To find the value of n, we need to divide the gap between the lines on the diffraction grating, which we have used, which is 300 lines per millimeter, divided by the total wavelength of the light. All right, so we know the wavelength, which is 600 nanometers, and we need to figure out the gap between the two consecutive lines. Okay, but the information we have is 300 lines per millimeter on our diffraction grating. So what is the gap between each line? So we know that in 1 millimeter there are 1 is to 10 raised to the power minus 3 meters divided by 300. Okay, this is the gap between two consecutive lines. Okay, so what we will do is we will keep this numerator as the value of our d, and we'll divide this by our lambda, so which lambda is 600 nanometers. 600 into 10 raised to the power 9 minus 9 actually, because we have nano. Now this will give us the value of n equals to, let me calculate it. So we have 1 into 10 raised to the power minus 3 divided by 300 divided by 600 into 10 raised to the power minus 9, and we are getting 5.55. All right, 5.55. So what is the total number of intensity of maxima from the grating we are going to get is, and just because they are, so you will be getting 5 maxima on the upper side of the center maxima, and the mirror image of that. Okay, so you will be getting 2 times 5.55 maximas. Okay, because what you are getting above the center maxima, the same you will be getting on the bottom side of the center maxima. All right, so to calculate the maximum number of maximas, maximum number of maxima is equals to 2 times n. All right, which is equals to 2 times 5.55 is approximately equals to 11 if we round off. So we have option C, which is the right option.